Good morning, all.
Hmm.
I have uploaded two videos. One is based on centroid of areas. There are two examples are solved in that. And the second one is related to chapter 6, that is moment of inertia. So I have posted these videos in MS Teams. Have you seen? Have you seen these videos?
Yes, sir.
Okay. So if you have any difficulty, especially in moment of inertia, so you can please ask. Okay, we can discuss those difficulties. So now today we are going to start with the 7th chapter, that is friction. So with this chapter, that is friction, we are going to complete the second unit. So for the first unit test, you have this unit 1 and unit 2, right? So we are going to discuss in today's session, what is friction? What do you mean by friction? What are the types of friction? And what is limiting friction or maximum friction? What are the Coulome's laws of friction? And we are going to see different situations or different cases. And what is angle of friction? This angle of friction is represented by the symbol phi. And what do you mean by cone of friction? And what is angle of repose, denoted by theta? And what is free body diagram and belt friction? Okay. So this friction topic, I hope you have studied. Everybody knows the basic things about friction. So can anyone tell me what do you mean by friction? Anybody?
Friction is a type of a
So it is
force
the force
which
which
opposes the
opposites
motion.
for the motion of the body.
Is the force which opposes the motion of the body, right? So friction is the property of surface of the body by virtue of which it offers resistance to the motion of the body. It offers resistance to the relative motion or impending motion of the body. So this force which opposes the motion of the body is known as friction force. So the direction of friction force is always in the opposite direction of motion of the body or opposite direction of impending motion of the body. What do you mean by impending motion? Impending motion. So impending motion is the state of the body in which the body is about to move on the verge of motion. On the verge of motion. That means you can say that when it is in impending motion, body is in impending motion, you can say that the body is in limiting equilibrium. So equilibrium means body is not moving, it is at rest. And if the body moves, you can say that it is not in equilibrium. But in limiting equilibrium, the body is at rest. Body is not moving, but about to move on the verge of motion. That condition is known as limiting equilibrium. Is it clear? Now, what are the different types of friction? Basically, there are two types. Dry friction and fluid friction. Dry friction exists between the two dry surfaces or between the two solids or between the two bodies, whereas fluid friction exists between the fluid particles of liquids or gases. So dry friction is mainly because of the surface roughness, because of the surface irregularities, whereas fluid friction is mainly because of the cohesive forces or the intermolecular forces between the particles of the fluid, right? But in this topic, we are going to study only dry friction. So in dry friction, further there are two types: static friction,
Static and kinetic.
right?
Static and kinetic.
Static friction and kinetic friction. So static friction is the friction between the two bodies when the bodies are at rest. Whereas kinetic friction is the friction between the two surfaces, between the two bodies when they are in motion. Right. So we can find that the static friction is always greater than the kinetic friction. This is because when the bodies are at rest, there is proper interlocking between the surface irregularities of both the bodies. When the bodies are at rest, there is proper interlocking between the surface irregularities. Hence, the resisting or opposing force to the motion is more. But if one body is moving on the surface, then there is no proper interlocking between the surface irregularities. Am I right? Hence, the resisting force to the motion of the body is less. Hence, the kinetic friction is less than the static friction. Now, what do you mean by limiting friction? So, this limiting friction is the maximum friction.
Yes, sir.
Yes. Now, let us consider a body which is kept on a horizontal surface. Say W is the weight of the body. Now, in this condition, this body is in equilibrium or not. Simply body is kept on the surface. So the body is at rest. It is in equilibrium. So what are the forces acting on the body?
Normal and weight.
No.
Right. So weight of the body, which is acting vertically downwards. Because of this weight, the body tends to move vertically downwards, which is prevented by the surface by offering a normal reaction in the opposite direction. So it is a normal reaction offered by the surface. So this body is in equilibrium under the action of these two forces. So when it is in equilibrium, you can say that the weight of the body is equal to normal reaction, summation Fy is equal to 0, right? Now, the body is not moving. It is not having any tendency to move. It is in equilibrium in y direction. Therefore, there is no friction. At this moment of time, the friction force between the surface and the body is 0. Am I right? Because these forces are not having any tendency to produce motion. Hence, the friction is 0. But when you apply a force P, say in horizontal direction, and this force is not sufficient to produce motion, you are applying force P, but it is not sufficient to produce motion. That means the body is at rest only. Am I right? That means it is in equilibrium, which means that this applied force P must be balanced by the force having same magnitude in the opposite direction. So that force is developed between the body and the surface because of friction. Am I right? Which is known as friction force F. Now this body is in equilibrium even in horizontal direction. So when you say that the body is in equilibrium in horizontal direction, summation Fx is equal to 0. That means here the magnitude of friction force is equal to the applied force P. Am I right? See, when the applied force is, for example, 5 Newton, the body is not moving. It is not having any, it is not moving, means it is at rest, in equilibrium. So the magnitude of friction force is also 5 Newton. Now I have increased this to 10 Newton. Still body is not moving. So to balance the 10 Newton, the friction force developed must be 10 Newton. So as you increase the applied force, the magnitude of friction force is also increasing, but there is a limit. Suppose when you increase the force, applied force up to 15 Newton, see, when the force applied on the body is 15 Newton, then the body is, say, in impending motion. Means the body is on the verge of motion, about to move. At this instant of time, the magnitude of friction force is also 15 Newton because it is in equilibrium. Right? It is not moving, but about to move. But it is the condition of limiting equilibrium. So in this condition, the friction force is 15 Newton. Now further, if I increase the force to say 16 Newton, then what happens to this body? The body moves. Am I right? When it is 15 Newton, it is about to move. When I increase to 16 Newton, the body moves. Once the body moves, the magnitude of friction force here is decreases. It is less than 15 Newton because 15 Newton is the static friction when the body is at rest. When the body moves, we know that the kinetic friction, it decreases because there is no proper interlocking between the surface irregularities. So the maximum friction force which you are getting is 15 Newton in the condition of limiting equilibrium when the body is in impending motion. So this maximum friction is known as limiting friction. Understood? So limiting friction is the friction force developed when the body is in impending motion, when the body is in limiting equilibrium. Okay. Now Coulome's laws of friction. So there are 4 laws, you can say. One is the friction force always acts in the opposite direction. Opposite direction of motion of the body, impending motion of the body or relative motion of the body. Now the magnitude of friction force does not depend. The friction force does not depend on the area of contact. Area of contact between the body and the surface. Third, the magnitude of friction force depends on the normal reaction. It depends on the normal reaction, but it does not depend on the area of contact of the body with the surface. And the fourth one, most important, the limiting friction is directly proportional to the normal reaction. What do you mean by limiting friction? It is the friction when the body is in impending motion, when the body is on the verge of motion, when the body is in limiting equilibrium. So limiting friction is equal to the proportionality constant, that is mu into normal reaction. This proportionality constant mu s is known as
Coefficient of static friction.
right. So it is coefficient of static friction. Now this is when the body is in limiting equilibrium. Suppose if the body is in motion, then you have the friction force is equal to coefficient of kinetic friction into normal reaction. So here mu k is coefficient of kinetic friction. Right? So we know that the coefficient of static friction is always greater than the coefficient of kinetic friction. So whenever you are using this, friction force is equal to mu s into normal reaction. That means that friction force is limiting friction. Point to be noted. FL is equal to mu s into normal reaction. Now there are different cases or situations. Now let us see the first case. The forces acting on the body are not having any tendency to move the body along the surface. Here, what are the forces acting on this body? Applied force P, vertically downwards, and weight of the body, self weight of the body. So if you draw free body diagram of this body, you have weight of the body, W, acting vertically downwards, applied force P, also acting vertically downwards, and the normal reaction offered by this surface, N, or vertically upwards. So in Y direction, in a vertical direction, the body is in equilibrium. So summation Fy is equal to 0. So you have normal reaction is equal to P plus W. Now, is there any friction between the body and the surface? Because along the surface, the body is not having any tendency to move. Hence, the friction force between the body and the surface is 0. Right? Now, in second case, the forces acting on the body tend to produce motion along the surface, but not sufficient to produce the motion. So here force P is acting horizontally towards right. So this force tends to move the body, but the magnitude of that force is not sufficient to produce the motion. So when you do a free body diagram, what are the forces acting on it? Weight of the body acting vertically downwards, the normal reaction offered by the surface vertically upwards, and the applied force horizontally towards right. Now in Y direction, body is not moving, it is in equilibrium. So summation Fi is equal to 0, normal reaction is equal to weight of the body. But in horizontal direction also, this force is not sufficient to produce the motion. That means body is in equilibrium. So this force, applied force P, is opposed by this friction force. Because the body is tending to move along the surface, and the friction will develop between the body and the surface in the opposite direction of the tendency of the motion of the body. Right? In this particular case, body is in equilibrium. Neither the body is moving in vertical direction nor in horizontal direction. Now here, the magnitude of friction force is equal to the applied force. Right? When the body is in equilibrium. See, in the first case, the forces are not having any tendency to move the body, hence the friction force is 0. In the second case, the applied forces are not sufficient to produce the motion, Here the magnitude of friction force is equal to the applied force. So the third case, the forces acting on the body are just sufficient to produce motion along the surface. Just sufficient to produce motion. What is the meaning of this? Is the body is on the verge of motion. Means body is in impending motion. So if you draw a free body diagram, weight of the body, normal reaction from the surface, applied force P, but the body is in impending motion, means it is in limiting equilibrium. It is about to move. So when the body is in limiting equilibrium, the friction force becomes maximum, which is the limiting friction. Am I right? So in y direction, the normal reaction is equal to weight of the body because it is in equilibrium. In a horizontal direction, also it is in equilibrium, but limiting equilibrium. Here, the magnitude of friction force is equal to limiting friction, which is equal to, yes, coefficient of static friction into normal reaction. Okay. So in fourth case, the forces acting on the body causes motion along the surface. That means the body is in motion. So it is not in equilibrium. Then if you draw a free body diagram, you have weight of the body, normal reaction, applied force P, but body is in motion along the surface. So this is the friction force F. In y direction, that is normal to the surface, there is no motion. It is in equilibrium. So summation Fy is 0, that is normal reaction is equal to weight of the body. But in horizontal direction, it is not in equilibrium. It is in motion. So here the magnitude of friction force is equal to coefficient of yes, kinetic friction into normal reaction. Right? See, in the first case, forces are not having any tendency to move the body, friction force is 0. In second case, forces acting on the body tends to produce motion but not sufficient, then the magnitude of friction force is equal to the applied force. Third case, the forces are just sufficient to produce, body is in limiting equilibrium, so magnitude of friction force is equal to limiting friction, µs into normal reaction. Fourth case, body is in motion, then the magnitude of friction force is equal to coefficient of kinetic friction into normal reaction. You have to remember this. You please note down. Let F be the force required to maintain equilibrium. Force required to maintain equilibrium of the body. And Fl is the limiting or maximum friction. If F is less than Fl, then what is your conclusion? Yes, the force required to maintain
Body is
equilibrium.
Body is at rest.
Body is at
Body
rest.
is at rest.
Body is at rest. That means the body is in equilibrium.
Equilibrium.
the condition of the body is equilibrium. If F is equal to FL, then
Impending motion or limiting
Equilibrium.
equilibrium.
Impending motion.
body is in impending motion. That means the body is in limiting equilibrium. So it is in equilibrium means at rest. So limiting equilibrium means it is also at rest, but impending its motion, on the verge of motion, about to move. Suppose if F is greater than FL, then what is your comment? The force required to maintain
The body
equilibrium
moves
is
and
greater
the
than the
opposite
limiting
kinetic
friction.
friction.
Right. That means the body is in motion, not in equilibrium. Suppose in the given example, if they ask, determine whether the body is in equilibrium or not, then what you have to do? You have to find out first the force required to maintain equilibrium, and that is to be compared with the limiting friction. So as per that, you can state whether the body is in equilibrium or limiting equilibrium or in motion. If it is in motion, what is the magnitude of friction force? Coefficient of kinetic friction into normal reaction. If it is in limiting equilibrium,
reaction.
magnitude of friction force is limiting friction, that is coefficient of static friction into normal reaction. If the body is at rest, the magnitude of friction force is equal to the upright force, right? The resultant force, you can say. Now, angle of friction, phi. Now, let us consider this situation. A body of weight W is kept on the horizontal surface, and a force P is applied on the body such that the body is impending its motion. Means the body is on the verge of motion. Then if you draw free body diagram, what are the forces acting on it? Self weight of the body vertically downwards, normal reaction offered by the surface, let us say NR, applied force P horizontally towards right. As the body is impending its motion, we have a limiting friction, say FL, in the opposite direction. Now, the resultant of this normal reaction and limiting friction is, say, R. The angle made by this resultant of normal reaction and limiting friction with respect to normal or vertical is known as angle of friction phi. Angle of friction. See, all these points are important, especially for this online examination, MCQs. So angle of friction is defined as the angle made by the resultant of normal reaction and limiting friction with respect to the normal reaction. That is angle of friction. Suppose, so this is the normal reaction. You have limiting friction. This is the resultant of these two. So this side indicates the limiting friction. We are saying the angle made by this resultant with normal is the angle of friction. Now from this right angle triangle, tan phi is equal to limiting friction upon normal reaction. But limiting friction is coefficient of static friction into normal reaction upon normal reaction. So you get tan phi is equal to coefficient of static friction. Means tan of angle of friction is equal to coefficient of static friction. So sometimes in the numericals, they will say the angle of friction is 25 degrees. Then you have to calculate that the coefficient of static friction as tan 25. Understood? Then cone of friction. So the same situation, that the body of weight W is kept on the surface, force P is applied on the body horizontally. Say body is in impending motion. Now, if you draw free body diagram of the body, you will have normal reaction offered by the surface, weight of the body W, applied force P, and the friction force, which is the limiting friction. And there is a resultant of these two. Now, if this force P is rotated in horizontal plane, that means the P is rotated about the vertical axis. So P is rotated about vertical axis in a horizontal plane. Then what will happen? This resultant will generate a cone. Right? So it will generate a cone. You are rotating P in a horizontal plane, which is applied on the body. Then this resultant will also rotate about vertical. So it will generate a cone known as cone of friction. So cone of friction is the cone generated by the resultant of normal reaction and limiting friction when the applied force P is rotated in horizontal plane. Now, we know that the angle made by this resultant with normal reaction is angle of friction. And we have this as limiting friction. Now, from this figure, you can write the properties of cone of friction. So what are the properties of cone of friction? The base radius of the cone of friction gives you the limiting friction, right? This radius is the limiting friction. Then semi-apex angle, semi-vertex angle of this cone is the angle of friction, right? This is phi. And the height of cone, gives you what? Normal reaction. Then the generator of the cone is the resultant of normal reaction and the limiting friction. So this R is the generator of the cone. So these four are the properties of cone of friction. Is it clear? Now angle of repose, that is theta. So here a body of weight W is kept on the horizontal platform, and this platform is hinged at one end. That means this platform can be rotated about this support. Suppose if you are increasing or if you are rotating the platform in anti-clockwise direction, you are rotating the platform in anti-clockwise direction, then the tendency of this body to slide down the plane, slide down this platform will increase. Am I right? So in this position, the body is not having any tendency to slide along the surface. Platform is horizontal and you are increasing, you are tilting the platform. Then as the angle theta is increasing, the tendency of this block to slide down the plane increases. Now you have to tilt the horizontal plane such that this body is on the verge of sliding. That means the body is in impending motion. At this state, this angle made by the platform with horizontal is known as angle of repose. So angle of repose is defined as the angle made by the platform with respect to the horizontal when the body is on the verge of sliding down under its own weight. Remember, no external forces are acting on the body. The body tending to slide down because of its own weight, right? Then that angle made by the platform with horizontal is known as angle of repose. Suppose if you draw a free body diagram of this block at this stage, tell me now what are the forces acting on the body? Weight of the body, which always acts vertically downwards. Then normal reaction offered by the platform. So it is perpendicular to the plane. That is perpendicular to the plane of platform, right? And the body is impending its motion down the plane, tending to move down the plane. Hence, the friction force will act up the plane. Being it is in impending motion, this is limiting friction. Is it clear? So these three forces are acting on the body. And this body is in equilibrium or not? Of course, it is in equilibrium. It is in limiting equilibrium, about to move, but not moving. So applying the conditions of equilibrium, taking x-axis along the plane, y-axis perpendicular to it, we'll find that this angle is theta. Then the component of weight in y direction, that is the component adjacent to the angle, is W cos theta, and other perpendicular component W sin theta. Now writing conditions of equilibrium, equations of equilibrium, say summation fx is equal to 0. So taking towards right positive, left negative. So we have minus W sin theta plus FL is equal to 0. So FL is equal to W sin theta. Say equation 1. Now writing summation Fy is equal to 0 plus NR, that is normal reaction acting upwards, minus W cos theta is equal to 0. So normal reaction NR is equal to W cos theta. Say equation 2. Now equation 1 divided by equation 2. W sin theta upon W cos theta is equal to FL upon normal reaction. So sin theta upon cos theta, tan theta. FL is nothing but coefficient of static friction into normal reaction upon normal reaction. So you have tan theta is equal to mu s. That means tan of angle of repose is equal to coefficient of static friction. You can say angle of friction is equal to angle of repose. Phi is equal to theta. Any doubts? Next, free body diagram. So many times we have used this term, free body diagram. So what do you mean by free body diagram? See, free body diagram is the diagram of the body under consideration of equilibrium, which is free, which is isolated from the system, showing all the forces acting on the body. So free body diagram is the diagram of the body which is isolated from the system under consideration of equilibrium, showing all the forces acting on the body. So what are those all the forces? There are three types of forces generally act on the body. One is applied force, applied forces or external forces. Two, reactions. We have studied the normal reaction. So in the previous examples. So there are different types of reactions that we are going to study in the analysis of bodies in equilibrium. Means these reactions are developed by the supports to maintain equilibrium under the action of applied forces. Right? We are applying forces on the body to maintain equilibrium. The supports will offer reactions. And the third type, the self weight of the body, if any. Self weight of the body, if any. So these three types of forces generally will act on a body in a system which is in equilibrium. Now consider this figure. So here there are two blocks of weight W1 and W2 and kept one over the other, and both the blocks are kept on the horizontal surface. So it forms a system, and this system is in equilibrium. So this system is having three bodies. Am I right? What are those three bodies? W1, that is body 1, body 2, and the ground or surface, you can say. Now the entire system is in equilibrium. Now we have to draw free body diagram of, let us say this is body 1, body 2. So FBD of body 1 means what you have to do, this body 1 is to be isolated. It is to be removed from the system. So this body 1 is having contact with body 2, right? So this body 2 is acting as a support to the body 1. So wherever there is a contact, there is a reaction between the two bodies. So when you draw free body diagram of body 1, what are the forces acting on it? I told you three types of forces. One is applied forces. Here applied forces are 0. There is no any external force acting. Then second is normal reaction. Third is self weight. So the self weight of the body is W1, which is acting vertically downwards. And this body 2, where the body 1 is having contact, will offer a normal reaction. So I will say N2. So it is a normal reaction offered by the second body on the first, right? So this body is in equilibrium. So writing summation Fy is equal to 0, you have N2 is equal to W1. Now when you draw free body diagram of body 2, now this body 2 is to be removed from the system. So body 2 is having contact with body 1 as well as the ground surface. Am I right? And both of these contacts are acting as simple supports. So when you draw free body diagram of body 2, self weight of the body, say W2, there is no externally applied force. And the reaction from body 1, normal reaction from body 1, I will say N1. Are you getting my point? N1 is the normal reaction offered by body 1 on 2. When you are considering body 2, you have to consider the effect of other body on it. That is effect of body 1 on body 2. That is N1. And the ground surface, it will offer normal reaction, I will say Ng. Now this body is in equilibrium. So writing summation Fy is equal to 0. You have minus N1 minus W2 plus Ng is equal to 0. Here Ng is equal to N1 plus W2. Now see, when there is a contact between the two bodies, each body will exert a force in the form of normal reaction on the other. So this body 1 is offering N1 on the body 2, and body 2 is offering N2 on body 1. To maintain equilibrium, these two reactions must be equal in magnitude and they are opposite in direction. Then only the system is in equilibrium, right? Otherwise system won't be in equilibrium. So as the system is in equilibrium here, N1 is equal to N2, but N2 is equal to W1. Therefore, Ng is equal to N1, that is W1 plus W2. The sum of the weights of both the bodies is nothing but the total normal reaction offered by this surface on the system. Then only the system is in equilibrium. So simply, free body diagram means it is the diagram of the body which is isolated from the system considering the equilibrium, under the consideration of equilibrium, showing all the forces acting on it, means applied forces or externally applied forces, reactions, support reactions, and the self weight of the body. Is it clear? So this concept of free body diagram will be more clear while solving the numerical examples, right? Then the next one is belt friction. It is totally different topic. So first we will solve numerical examples on this plane friction, and then we will go for belt friction. So here there are total 4 types of numerical examples in the topic of friction. One is based on the planes, whether it is horizontal plane or inclined plane or vertical plane. Second one is ladder friction. Third type is wedge friction, and the fourth type is belt friction. Okay. Now let us see the first type, that is friction on planes. Please note down this example. 400 Newton block is resting on a rough horizontal plane as shown. Determine the force P required to cause the motion if applied on the block at an angle. There are 2 cases. The first case, theta is 0. Second case, theta is 30 degrees. Means in the first case, P is acting horizontally towards right. So the coefficient of static friction between the block and the plane is 0.4. So here, what should be the condition of this body? Determine the force required to cause the motion. Means the body should be in impending motion, limiting equilibrium. So this is the given figure. So let us draw free body diagram for the first case, that is when theta is equal to 0. Weight of the block is given 400 Newton. So you have self weight of the body 400 Newton. So the normal reaction offered by the plane, I will call it as NR, and the applied force P, theta is 0 here, and the body is in limiting equilibrium. You have to find out the force required to cause the motion. When the body is limiting equilibrium, the friction force developed is the limiting friction, which is equal to coefficient of static friction into normal reaction. As the body is in equilibrium, we can write summation Fy is equal to 0. So normal reaction is equal to 400 Newton. Writing summation Fx is equal to 0. To have P is equal to mu s into normal reaction. So mu s is given as 0.4 into 400. So the force required to cause the motion is 160 Newton. Right? Now for second case, when theta is equal to 30 degrees. So let us draw free body diagram again. Weight of the body 400 Newton. Normal reaction NR. Applied force P, making an angle 30 degrees with the horizontal. So if we resolve this into two components, X and Y components, X component is P cos 30, Y component P sin 30. And being it is in impending motion, there is a friction force, which is limiting friction, mu s into normal reaction. So for equilibrium, we can write summation Fy is equal to 0. So we have P sin 30, which is acting upwards, minus 400 plus NR is equal to 0. So normal reaction is equal to 400 minus 0.5 P. That is P sin 30. Now writing.
So 0.4.
What is 0.4?
No, sorry.
It is P sin 30. No? So writing summation Fx is equal to 0. We have P cos 30 minus mu s into normal reaction is equal to 0. So it is P cos 30 minus mu s is 0.4 into normal reaction, that is 400 minus 0.5 P is equal to 0. So solving this equation, you get force P.
240, sir. 240 Newton.
No. It can't be 240. Please check. It should be less than 160. Because the force P is acting upwards. No? So the normal reaction will be less.
Yes, sir. Yes.
So So it is 150. 150.1. Okay.